Speaker of the morning is Professor Bing Han from the University of Alberta, and he will speak on directional framelets with low redundancy and directional quasi-tight framelets.
Thank you. So first, I'd like to thank all organizers for inviting me. So I will talk about some topics, some old results and also some recent results on wave analysis. So the motivation is if I'm going to do some image processing, visual processing, and for problems in 2D, 3D, or higher dimensions. So a very important phenomenon is, for example, for images. So it's very, very important for your representation system to capture the edges. So for example, if you look this structure, so if you regard this image here, so not only you are trying to represent the function under a wavelength basis, but also you want, after you do some processing, you want to keep basically preserve the edges very well. So if I'm going to use a standard tensor product wavelength transform, you are going to see they have some problems. So one of this approach is using the framelets. So basically I'm going to report two different approaches. One is using a complex tight framelets, another one is a recent work by using a quasi-tight and dealing with high dimensions. So let me give you some definition first. So basically we are talking about multivariate tight framelets. Basically you take divide the integer matrices which are expanding. So means you take M to be any integer matrix whose eigenvalues have a modulus greater than 1. So the most popular choice for the dilation matrix is just the diagonal matrix with all the entries being 2. So this is called a dyadic dilation. This is the most popular choice. And then we are going to have a collection of square integrable functions in d dimensions. So basically we have a function phi and also psi 1 to all the way to psi s. So this basically is the later you are going to see is a refinement function, and the wavelength functions are here. So this generally is a tight M framelets in the square integrable function space L2. Basically means any function from this L2 can be decomposed in the framelet representation. And the wavelength elements is generated by the standard way. So we have a dilates as in the Seiko and the Young and when you guys talk. So we're dealing with a general dilation M2 to the J, not necessarily to be 2. You can, if this is coming to you, you can think about M just equals 2. So just dilated by 2. And then you also shift this function by in integers, multivariate integers. So you have wavelength functions. So any function, if they can be represented by this identity, then this collection of functions is called tight M framelets. So one of the major problems is how we are going to characterize such a collection of functions so that they satisfy this identity. So the convergence is unconditional convergence in L2. So the nice thing about this one, you don't need to assume any function to be refinable multi-resolution analysis. Basically, the theory will tell you, so if this is a tight M framelets, then this necessary and sufficient condition, you have basically 3 conditions. So the first one is the normalization condition, so the Fourier transform at 0 equals 1. So basically for nice function, this just means the integral of phi equals 1. So it's a normalization condition. And the second condition is you are going to see the failed banks. So so-called failed banks is sequences of little L2 sequences. And then the function phi and psi must satisfy these identities. So this is well known. So the first one written in the frequency domain, so the phi hat and M transpose of Kc equals the A hat. This is a 2-pi periodic function in higher dimensional 2-pi periodic function times phi hat. So this is known as a refinement equation in the higher dimension. So if you are familiar with the frequency domain, so basically the refinement equation is looks like something looks like this. So you have a k, you have a phi m of x minus k. So this k over zd. So this is a time domain refinement equation, and you can take the Fourier transform, and this one just becomes this frequency-based refinement equation. And the wavelength, once you know the refinement function, then the wavelength is actually coming from this refinement function through the high pass filter times with phi. So this is related to the multi-resolution analysis. It's a necessary and sufficient condition, and then all the field banks must satisfy these equations here. So, and I'm using this notation. So, filter just means a sequence of Veneto L2 sequences, and you can put them into the Fourier transform. You are going to get a two-periodic function. So, you are going to see in the construction of a tight framelets. So, basically, we're starting with a field bank. So, basically, a sequence of filters. They satisfy these complicated nonlinear equations. So that's why we call the tight M-framelet field bank, means they satisfy these identities. So if they satisfy this condition and we have a tight framelet field bank, then we can define a refinement function through this relation here. So from this A, we can define a function in the frequency domain, get a function, and then after we define phi, then we are using high-pass filter to get this place L. And then this theory will tell you this one will satisfy this condition, get a tight framelets. So the hardest part you are going to see, we have many constructions, but not all these kind of constructions will work equally well. So the second question, the major question about the construction is so if I'm going to construct tight framelets, then the major problem is how you are going to solve this type of equations. Because all of them are two-periodic, multivariate trigonometric polynomials, they must satisfy this identity. And so there are two issues here. And the simplest way to construct a multivariate tight framelets is using tensor product. So this is the most popular approach. Tensor product is nothing else. You are using 1D function. So for example, in D dimension, you have a 1D function f1 to fd. So you just do the standard tensor product to get a multivariate function. And if I'm going to create a 1D tight framelet field bank, so you have a phi here place L to place S, you do the tensor product. Tensor product basically means every single element here tensor with any other one. So treat this as a set. So you do the tensor product, pick up one from this one for each dimension, and then form the tensor product. Then you are going to end up with a tensor product tight framelet field bank using the dilation. So the dilation matrix must be how to say it, must be a diagonal matrix. So I'm taking m equals 2d. So this generally is the simplest and the plainest way to construct tight framelets. And so some of you will say, well, once we build a 1D wavelets, we do the tensor product, we can handle all the questions. But the problem is if you are going to deal with image processing, actually this very simple tensor product tight framelets have two major shortcomings. The first one is the directionality here, and the second one is the translation invariance. So I will concentrate on the directionality. So what is the directionality really means? In an image, you have a lot of edges. You cannot require in an image all the edges should be horizontal or vertical. The edge could go 45 degrees, could go 15 degrees, so they can all different directions. And if you are going to use a tensor product, framelets or wavelets, you are going to see they can only handle the direction horizontally or vertically. If you are going to have an edge at other directions, then you are going to see after you perform the wavelet transform, they cannot be capture such directionality very well. So this is one of the major shortcomings, and there are a lot of different approaches. So people using undesignated wavelet transform, the curveness, sureness, contourness, dual tree complex wavelets. There are so many little approaches. I mean, I think people working in this direction for more than 30 years now, trying to improve the performance of standard tensor product real valued wavelets here. And also among all this kind of approach, people also actually trying to directly construct non-tensor product tight framelets, but this problem related to multivariate trigonometric polynomial and is very hard. So the approach we are taking is the old approach is very simple. We want to take the tensor product structure, so we're still using tensor product, but we want to achieve the directionality here. How we can achieve this one? So basically we don't use real valued wavelets. We are using a complex valued tight framelets and using tensor product. Then I'm going to show you a few examples. You are going to see the directionality is significantly improved. Another approach is that we are dealing with a multivariate directional quasi-tight framelets. So we are not dealing with the tight. So you are going to see, if you are going to construct a multivariate tight framelets, it's a very difficult problem. But if I'm going to relax a little bit, then you are going to see some a lot of beautiful math related to this. So let us just show you why the tensor product real value wavelength is not that good. So this example actually is here. This is a tensor, where no tensor in the second talk. So if I'm going to take this wavelength to the tensor product, this is a 2D. So you are going to see this averaging. This is a function phi. Okay, so phi tensor with phi. So basically the characteristic function of the unit square. So you have 3 wavelength functions. So you are going to see this is 1. So you are going to see you can capture the edge along this direction. So basically you have a different difference between this and this along the horizontal direction. Another one is along the vertical direction. But the third elements here don't have any directionality here. So that's why the tensor product real value wavelengths can only capture directions along the horizontal direction and the vertical direction very well. Even you have a 45 degree, this kind of system cannot do well about the capture any other directions. So our first approach is quite simple. So we're using complex approach. So this everything is the frequency domain. So the product here is not the filter, is the periodic trigonometric function. Okay, is a hat. So it's a periodic function. So the low pass filter will look like this bump function in the characterization of a function spaces. So the phi in your talk. So this is a high pass filters here, and so this one have 3 filters. So one is a low pass filter. So you have a B plus, you will also B minus. So 3 stands for you have 3 filters, 1 low pass, 2 high pass, and you can also do more. So this example actually you have a similar the low pass filter. So you have 2 low pass filters, and also have a 1 high pass on the positive part, and this filter on the negative frequency. So this is sort of related to the Hilbert transform. So you require your high pass filter only concentrated either on the positive frequency or negative frequency. You don't want the frequency concentrated on both the positive and the negative. So if you are going to have a filter which are real value filter, you take the Fourier transform, you are going to see the real value filter, the Fourier transform should concentrate on both negative and positive, because you can do a very simple calculation. The frequency should be equally on the negative and the positive. So because they only concentrate on positive or negative, so that's how come if I'm going to look the sequence of filters, the coefficients are complex numbers. They are not real valued coefficients. So that's where the complex tight frame is coming from. And once we have this 1D tight frame field bank, then what we do, we just do the tensor product here. And then you can do it in tensor product in 2D, 3D, and higher dimensions. And then you can separate the real and imaginary. So let me show you the tensor product in 2D. So this using the CTF3 complex tight framelets using 3 filters. So you are going to see the first 4 are real part of the system, and the last 4 is the imaginary of the, because all the functions except phi, they are complex valued functions. So you can separate them as the real part and the imaginary part. So you are going to see they do have a much better directionality. So this is horizontal direction, this is a 45 degree, this is vertical direction, this is negative 45 degree. So you achieve 4 direction compared with the 2 direction of tensor product. And also you can use CTF4. So CTF4 actually have more directions, so they have more than 6 directions. And also you can do a little bit more, so because you can keep increasing the number of filters. So this is just 3 and 4. We can also use 6. So this is 6. So you have 2 low pass filters here. So this is a low pass filter concentrated on the positive frequency. This is a low pass filter concentrated on the negative frequency. And we have 2 high pass filter concentrated on the positive frequency, and also have 2 high pass filters concentrated on the negative frequencies. So we total have 6. So we have 2 high pass filter on this side, and 2 low pass filter, and also 2 negative concentrated on the negative frequency. So total 6. And if I'm going to do the tensor product, you are going to see this very nice system. and you are going to see they have a good mixture about the directionality here. So we have 6 direction, and also they also have a texture. So because for a lot of image processing, not only you are going to see the image have a lot of these edges here, you could have a texture. For example, if I wear these sweaters, you are going to see they do have textures. So you are not only try to capture the edges very well, but sometimes we also need to capture the textures very well. And using the complex tight framelets approach, you are going to see actually we can achieve the directionality here. And so in the next few talks, I'm going to show you whether, because this is more or less more applied. So we have many choices of tight framelets. They could satisfy the regularity condition, they could satisfy the vanishing moment condition, complex support, many nice properties. But if I'm going to apply all these kind of tight framelets to a particular applications, they are not equally created, because one of them is performs much better than the other one. So let me just show you a few examples here using this system. So there are a lot of comparison with other known approaches. So one of these famous ones, this indeed dual tree complex wavelet transform actually is coming from the Department of Compute, is by Kingsbury from Department of Computing Science at this University of Cambridge. Actually, he proposed this dual tree complex wavelet transform by using the Hilbert transform, and this actually performs very impressive. So they call it dual tree. Dual tree basically means, let me quickly explain to you what the dual tree means. So standard the wavelet transform have one low pass and one high pass. So this is one tree. You have a low pass, high pass is only one tree here. So the dual tree actually using another coordinated orthogonal wavelet transform. So basically you go two directions. One is complex for the real part, another wavelet transform for the imaginary part. You are going to put these two trees them together, mix them together, then you form a very nice dual tree complex wavelet transform by using the Hilbert transform, and they can achieve the directionality very similar to this one. So if I'm going to plot the elements in the dual tree complex wavelet transform, then you are going to see it actually looks like almost identical to this, even though this is not the dual tree complex wavelet transform. Okay, so this is dual tree. And another one is our approach using the tensor product complex tight framelet CTF6. And the people also, in order for the denoising problem, people not only using the discrete wavelet transform, they actually use the undecimated discrete wavelet transform. So basically they don't do the down sample by 2. So you are going to see this indeed is a framelet approach with a high redundancy. And also there's another famous research using the total variation. So it's a Rudin, Ausher, Fatamis, RF model using high order schemes. And also they have some sheerness and curveness approach. So in the engineering literature, how you measure the performance, basically they using the so-called peak singular to noising ratio scale. Now it's because it's a mean square error scale in the denominator. Okay, so you are going to the smaller the mean square error, the larger this PSNR, and because it's a log here. So if you are going to achieve the improvement over, for example, 0.2, because it's a log effect. So generally, if you are going to improve the performance by 0.2 to 0.5, it's regarded as a significant improvement, because it's a little log. So if you look this one, so let us look at the denoising problem for the Barbara images here. So if I using the undecimal wavelet transform, then you are going to see this noise level. This sigma is the standard deviation. The larger the standard deviation, the heavier the noise. So you are going to see this performance by using undecimal wavelet transform. This is Kingsbury's approach by dual tree complex wavelet transform. This total variation, this sheerness, and this our performance. So in the black color bold face letter means the best performance. So if I'm going to compare this with the sheerness, then actually the performance is much better than the sheerness. And not only here, so what is the redundancy? So if I'm going to give me one image here, for example, 512 by 512, and you do the framelet transform, you are going to get a lot of coefficients. So this is the rate of the, so for example, the for redundancy means if you have one image here, you do the dual tree Commons wave transform, you are going to get the coefficients of the 4 sides of the image. So original data is n, total number is n, then you are going to get the coefficients for n. So if I'm going to deal with the sureness, the redundancy rate is very high, it's 49. So means the original data is n. After you do the decomposition, you are going to get 49 times n coefficients. So now for our system, our redundancy rate is only 10.7. And so this is for image processing. Now if I'm going to do the video denoising and 3D problem, you are going to see the redundancy is much higher. So that's why if your redundancy is higher, then the speed is significantly slower. So that's how come it's very important also to reduce the redundancy for faster computation. So all this kind of approach, if you do it for, in particular, if I'm going to use a sureness in 3D, actually the computation is very slow. So it could take you, the decomposition level could take you sometimes 1 hour to do a full transform. So because the redundancy is huge. And so this is also another application using the so-called image inpainting. So for this original image here, so you have a lot of pixels missing here. So basically you are going to have around 80, I think for this one, 80% of the pixels are missing. So for all the image size, so you throw away 80% of the pixel numbers randomly. You can still reconstruct this image by using inpainting. So this reconstruct one from this, even though you are missing 80% of the pixel data. And also you can erase some the inpainting. You can also have a noise. You can also have a write words here. You can, so this given image here, this is a true image. So you can actually perform the transform, or even with this noise level 20, you can still reconstruct from this one to get a reconstructed one by removing this words here. So what I can see for the complex tile framelets, generally speaking, they perform much better than most known approaches, including the curveness, sureness, dual tree, complex wave transform. And the approach is take advantage of the tensor product and also takes advantage of the wave transform, the standard wave transform. The only difference between the framelet transform and the wave transform, we are using more than one high-pass filters. Okay, so this is the only difference. Now, in order to reduce the redundancy for high-dimensional problems, so the idea is actually fairly simple. So let us just look at the wave transform. So standard wave transform have only one low pass and one high pass. Now, because we are dealing with framelets, so we have more than one high-pass filter. So originally, people using this downsample by 2. So when I mentioned about the undecimal wave transform, people don't do the downsampling. Downsampling means you have a sequence of numbers. You only keep the coefficients at the even position. For example, you only keep the coefficient at 0, 2, 4, 8. So you throw away all the position as the odd position. So that's how come the data is shrunk by half. So now the trick, in order to achieve low redundancy, basically we are using higher sampling rate. We can use the downsample by 4. So means we only for every sequence we only keep the position at the multiple of 4. So 0, 4, 8. So you are going to see the original data is shrunk by 1 over 4. So you are throw away a lot of data. Then we still can get a perfect reconstruction here. And so the redundancy, after you do this one, then you are going to see the same system. So for example, the tensor product complex tile framelets. So in 2 dimensions, the redundancy is only 2. In 3 dimensions is hold on. So this the 1 dimension is 2. So 2 dimension is 2.7. 3 dimension is 3.7. In 4 dimensions is only 5. So the redundancy rate is very low compared with so this kind of system is suitable for 2D, 3D. Even I think if even you go to 4 dimensions, it's also quite feasible because the redundancy rate is very low. So I will only show you one example here. So if I'm going to do the video processing, you are going to see the redundancy rate for sureness for 3D problem is 154, and the another design of a share system is 42. So the surface needs I think is developed many years ago by engineers is 6.4. So this original complex tight framelets is almost 30 here, but this one in 3 dimensions is only 3.7. And also the performance compared with the sheerness here. So if I'm going to compare the performance of the redundancy complex tight framelets with the sheerness, you are going to see sometimes our improvement could be 7 dB regardless they have a huge difference than our algorithm and this algorithm here. So but the main talk of this this talk is not on this image process, this old work. So using a tensor product, actually we can achieve a better directionality here. But if I'm going to deal with, for example, you want more directions, so the tensor product put a very intrinsic restriction about the directions. So a major problem is I want to improve the performance using a better resolution of the directions. How we can do this? We cannot use the tensor product. So we have to handle the multivariate tight framelets. But the construction of a multivariate tight frame is very, very hard because you are going to see later on. Then, in order to construct a tight framelets, you are going to see they relate to the Figure risk lemma and also matrix value Figure risk lemma. And but this only holds in 1D, not even in 2D. So to overcome this problem, I'm going to introduce a very interesting notion here. We want the system looks like a tight framelets, but not tight framelets itself. So by what I mean is almost looks like a tight framelets, but not tight framelets is because if you look this reconstruction, every function f can be reconstructed in almost the same way except this little epsilon L. So if I'm going to set this epsilon L to be 1, this exactly is a tight framelets. So what I want, I'm going to allow this epsilon L to be a +1 or -1. I'm going to allow myself a little bit of flexibility. So this epsilon L could be +1, could be -1. Then this is called quasi-tight because this behaves, looks like very similar to the tight framelets. So this is only a small change. So if this is 1, this is a tight framelets. If this is +/-1, then it's a quasi-tight. Now, if you have the quasi-tight, you are going to see for the higher dimensional construction of multivariate quasi-tight framelets is very flexible. So this construction, so similar phenomenon. So in order to construct quasi-tight framelets, so everything is boiled down to solve this nonlinear systems. So if we can construct the quasi-tight framelet field bank, then we can get a refinement function and define the wavelengths in the standard way. Then we are going to get a quasi-tight framelets. So we are going to solve this one. Now, because we know this epsilon to be plus and -1, so the solution now is very simple. So and you are going to see why it looks like a tight framelet. So this is one example. So the motivation for us to study the quasi-tight actually originally from my book. When I wrote this book, I actually construct excellently counter in this example here. They are dual framelets, but looks like the tight framelets. So this is the first example I ever saw in the construction in 1D. So if you look the graphs here, you are going to see there's no difference between tight framelets or quasi-tight. So these refinement functions are the same. And the second function is this +1. So this is a negative +1 because we know the sign change. So this +2, this is exactly +2. So if you are going to get a tight framelets, this exactly will be +1, not a negative +1. This is the only difference between the tight framelet field bank and the quasi-tight framelet field bank. So in this framework, you are going to see if we are going to use the quasi-tight framelets to replace tight framelets, you are going to see the results is actually, theoretically speaking, is very beautiful. So the first one is for any dimension matrix, for any complex supported refinement function, we can always construct a quasi-tight framelets with directionality. And the high-pass filter looks like have only 2 points, very similar to the high. So high have only 1 and -1. And this all high-pass filter takes just 2 points. One is C, one is -C. So they have a naturally 2 points construction. So because you have a 2-point construction, this automatically gives you the directionality here. And not only here, if I'm going to see my low-pass filter A, all the coefficients of A are non-negative, actually we can construct a directional tight framelets. So this is including the Haar. The Haar filters indeed everything is just 1, 1, 1, 1, 1 anywhere, non-negative coefficients. And the masks for all the box spline functions, they are non-negative. So we can construct this directional quasi-tight framelets. So just give you a few examples. So this 2D. So you are going to see in this example, the high-pass filters only have 2 points. So you are going to see, except this, you have a coefficients here. You have a -1, -1, +1, -1, +1 for all these kind of filters. And this one gives all the directions. So this is a vertical direction, and this horizontal direction. This is 45. This 45 degree. This is also another negative 45 degree. And you can also look this graphs here. You can see it clearly. All of them have a directionality. So the theory means there's no constraint anymore. You can construct quasi-tight framelets with directionality from any refinement functions in any dimension. Okay. So the next one is if you are going to try to achieve the mesh moments. So the same phenomenon here. So you are going to see from any refinement functions and from any dimension matrix, you can always construct a quasi-tight framelets with the highest order of mesh moments. And the nice thing about this one, originally we have a nonlinear system to solve, but this construction, you only need to solve linear equations. So basically, we'll convert a nonlinear problem into a linear problem. So this one example here in 2D. The construction is very simple. And this another example I will skip because I have only 5 minutes. So I want to mention to you why this multivariate question is hard. And some of you will say, well, I'm not working on wave analysis. This actually everything here dealing with multivariate trigonometric polynomials here. Why it's hard is because if you are going to see what is a quasi-tight framelets field bank, basically means that you have to solve this nonlinear system. So this definition here. And you can write this kind of equations into the matrix form, into a very nice matrix form. So you can put your filters using the so-called causes here. So in 1D you have one sequence. You are going to take the coefficient at even position. So 0, 2, 4. This is one new sequence, and also take the position at the odd position. So this is the causes at 1. And then you can form this they call a polyphase matrix here. And then this condition for the quasi-tight framelit field bank were equivalent to see this matrix of a trigonometric polynomial should satisfy this identities here. Is a Q times the diagonal matrix with 1 epsilon 1 to epsilon s. This could be plus minus 1, and this is conjugate and transpose. This should satisfy this identity. So this identity is equivalent to this the definitions here. Just rewrite this one, and we can also further rewrite this one by take out 1. So you are going to see the construction basically will becomes this problem. So generally speaking, A is given. So from this A, you construct this D by D matrix here, and then you need to split this D by D matrix into this form, but with epsilon 1 to epsilon s. Now, if I'm going to take the epsilon 1 to epsilon s to be 1, so for example, all of them is 1, this is gone. So this means that this matrix is it's a positive semi-definite matrix here. Then you have to split this matrix into a Q times Q transpose, commas Q star. So this is a well-known matrix factorization, or also called matrix vanilla Figure risk lemma. And everyone knows in 1D this is true, in 2D is no longer true. Not only here, you can also, this problem also related to the sum of squares. So you have a non-negative to you have a non-negative multivariate trigonometric polynomial. You are trying to write this one, the sum of squares of some trigonometric polynomials, and this results in the real algebra geometry is known to be true in 2D, but it's no longer true in 3D. So that's how come if you are going to see you are dealing with tight framelets, then all this epsilon 1 to epsilon s must be 1. So you have to do the spectral factorization, which is very hard. But if you are going to allow yourself the flexibility, and now this epsilon 1 to epsilon s to be plus minus 1, things is completely changed. And I will give you a few results. This is underline what in our constructions here. So you are going to, the results is quite general here. You are going to give me any Hermite matrix A of multivariate trigonometric polynomial. So Hermite matrix just means this condition is true. Then you can prove. You can always decompose this matrix A into a U times the diagonal epsilon 1 to epsilon s. Epsilon is only plus 1 or minus 1 times U transpose T. You can always do this for any multivariate polynomials. And as a consequence, if I'm going to give me a trigonometric multivariate polynomial, then you are going to see if this have satisfies this Hermite property, then you can write them as a source very similar to a sum of square, except you are going to allow yourself the epsilon L. Epsilon L could be plus 1, could be minus 1. This is always true. So this means, and also I should mention that in the engineering community, in the control theory, this type of decomposition actually is very, very important. So in the 1D case, and people in the engineering community actually started this problem in 1970s to 1980s, and indeed we can refine the results in 1D. So this last results just trying to see. I didn't mention about how large is this matrix here. So the matrix will be looks you have a D rows here, but you could have many columns, right? The matrix looks like a rectangle, but the rectangle could be very, very long. So the theory just tells you you always can do this, but the size could be large. In 1D, basically we can tell you what is the minimum of the size. So minimum of the size related to the eigenvalue of this matrix A is here. You are going to the minimum size is completely determined by how many the eigenvalues of A, how many positive eigenvalues and how many negative eigenvalues. So if I'm going to take the maximum number of positive eigenvalue and plus the maximum number of negative eigenvalues, put them together, this gives you the size of the U. So this is a necessary and sufficient condition. You cannot do it with a less columns. So we have a complete pictures here, and this is the generalization of the Fisher Risk lemma in 1D. And this minimum, so the minimum size is I think M1, M2 is the minimum condition. This is less than sufficient conditions. And the nice thing about this results is you don't require the matrix A to be non-negative. Any matrix satisfies this condition, you can do this factorizations here. So let me finish my talk. So basically in my talk I present two approaches. The first one using a complex tight framelets. Using tensor product, you can increase directionality in high dimensions, and it generally performs great. And the second approach is quasi-tight framelets. Once you are going to drop the framework of a tight framelets by allowing you a little bit of freedom using plus minus 1, actually the matrix factorization in higher dimensions is much more flexible. You no longer run into the theoretical barrier because matrix value, the Fisher Risk lemma is no longer true in high dimensions, but now we have the factorization in any dimension. So that's all what I want to talk about, and the reference here is given here just in case if you are interested. Thank you.
Would you like to ask any questions?
I take it that you are just having the sign changes with the epsilon plus minus 1 because other multiples, positive multiples, in the approximation can simply be absorbed into the size or into the inner products or something if you want to have other numbers to multiply with except for the sign change.
Yeah, sign change is basically because motivated by this examples here. So basically means if I'm going to have a multiple here, then you are going to we are dealing with the real value, the wavelength. So either the number is positive, you can take a square root. So you can evenly distribute it. If the number is negative, so you put a negative out and take a square root. So that's how come consider plus minus 1 is sufficient.
Exactly. For no further multiples, no further scaling is necessary.
Yeah, right.
More questions? Let us thank Professor Han for doing that.